This is lesson 1.6 for our Pre-Calc 12 class. Unit 1 is called Functions and Transformations. Lesson 6 is called Reflections and Stretches. In this lesson, we're going to talk about what's a reflection, what's a stretch, and how to identify those two things graphically and with function notation as well. In the last lesson, we talked about a translation as our first type of transformation. So reflection is also a type of transformation. A reflection just kind of, as the name suggests, reflects an image. You can reflect it over the x-axis, you can reflect it over the y-axis, you can do really any line you can do a reflection. So, yeah. The smiley face is not technically a function, but it is something we can put on a graph and look at and reflect. And Mulan reference, if you get it. So a reflection over the x-axis, when we're looking at function notation, the expression will have a negative sign, like as a negative on the output, or like a negative outside of the brackets, or radical, or whatever. It's something that you do at the very end. So when we look at any point on a function, x, y, a reflection over the x-axis would be to negate the y value. So x, y would become x negative y. So x values don't change, y values flip. So if our parent function for absolute value of x is a v, reflection over the x-axis will just make it upside down. Parent function x cubed, it's reflection over the x-axis. All the y values, so on the left, the y value is really low, so its reflection would be really high. And on the right, its y value is really high, so the reflection would be really low. So we just kind of get h of x, our reflection right here. Now, if we reflect over the y-axis, what we're doing with function notation is we basically have a negative coefficient on our input x. Inside the brackets is the negative sign. Any point on our function x, y, we are basically, to reflect over the y-axis, we're negating the x coordinate, or the input. So x, y becomes negative x, y. So when we flip it over the y-axis, the positive x values and the negative x values kind of switch places. So when we look at our parent function for absolute value, this reflection is identical to the original parent function, because the left side looks like the right side. When you flip it, looks like the same. The x cubed function, if we reflect it over the y-axis, let's see here. So on the right, it's up high. So then, if you reflect it over the y-axis, it would be up high on the left. On the left, it's down low. So again, the reflection on the y-axis would be on the right, down low. It's a different explanation and a different kind of reflection than x-axis. Coincidentally, for this parent function, x cubed, it looks just like the reflection over the x-axis, which is kind of cool, I guess. All right, so that's reflections. A stretch is another type of transformation. So we have translations, we have reflections, and now we have stretches. A stretch is a type of transformation that makes a graph narrower or wider. You can imagine putting your hands up and just smushing it vertically, or you can smush it horizontally. And you can create a stretch that way. The word stretch is a little ambiguous, because I don't know if I'm stretching it vertically or horizontally. Or if I say a vertical stretch or a horizontal stretch, I think that's still kind of ambiguous. So we're going to use the words vertical dilation and horizontal dilation. Dilation just means kind of like if it's expanding something. So vertical dilation, we're expanding it vertically. Horizontal dilation, we're expanding or dilating it horizontally. We look at vertical dilations with our function notation. It means we're multiplying the output by some value a. And a can be any real number. It just can't be 1, because multiplying by 1 doesn't really dilate at all. It could be a fraction like 1/2, it could be a whole number like 2, just not 1. And technically 0 doesn't work either, but we're not going to deal with those too much. So so any number outside of the brackets basically is a good hint that we have a vertical dilation. And so what it's going to do is the rule is it's going to change any point x, y on your curve or your parent function. It's going to take the output y and multiply that by that a value. So for example, here's our parent function f of x. If g of x is 2 times the absolute value of x, then our a value is 2. We are doing a vertical dilation because the 2 is outside of the absolute value symbols, which are our quote-unquote brackets in this case. So we're multiplying the output by 2. So the point 1, 1 on our parent function becomes 1, 2. 2, 2 becomes 2, 4. Again, the output's multiplied by 2. And so what we can see is we're dilating it vertically, and in this case it's being dilated by a factor of 2, so it's actually getting stretched vertically. H of x has a vertical dilation with an a value of 1/2. So we're just taking all the y values on our parent function and dividing it by 2, or multiplying it by 1/2, or cutting it in half. Either way, 1, 1 becomes 1, 1/2, 2, 2 becomes 2, 1, and so on. And so our vertical dilation is a scale factor of less than 1, so we're actually compressing it vertically. But it's still a vertical dilation. So we're messing with the outputs. Now, horizontal dilation is where we're gonna dilate or stretch this thing horizontally. So we have our parent function. A dilation you could see in function notation as any coefficient on the input x. And so notice the a is on the inside of the brackets. The dilation is going to result, any xy pair on the parent function is going to be the x value divided by that a value, or 1 over a times the x. And then the y value stays the same. So if the point 1, 1 is our parent function, it's going to be the x value divided by a. So for example, j of x has a 2 for its a value. It's a horizontal dilation because the 2 is inside the brackets, or in this case the absolute value symbols. And we're going to divide by 2, divide the x value by 2 to get our new image, or our new horizontal dilation. So 1/2, 1 would be a point on our j of x function. 2, 2 is parent function, so divide the 2 by 2, the x value by 2, we get 1, 2. So 1, 2 is going to be another point. And what we can see is we have this V, it's dilated horizontally, but we are compressing it horizontally. So we get a more narrow graph. J of x looks a lot like G of x. In this particular function, their graphs are identical. However, that won't be the case with any parent function. Okay, so k of x, we have an a value of 1/2. The a value is inside the brackets, right next to the x, this coefficient. And so we're doing a horizontal translation. We are dividing the x values of our parent function by 1/2. Dividing by 1/2 or multiplying by 2, same thing. So take any x value, double it. 1, 1 would become 2, 1. 2, 2 would become 4, 2, and so on. So then we create k of x is this much flatter line, or as we would say, we're horizontally dilating this thing as a stretch. All right, some examples here. So looking at reflections, when we're trying to find if there's a reflection on a function from the function notation, we're basically looking for negative signs. If the negative sign is inside the brackets, recall that means it's a reflection over the y-axis. And if the negative sign is outside of the brackets, it's going to be a reflection over the x-axis. And so you can take a look at these. You can see some examples. Notice example D, there is no reflection. The parent function is the square root of x. -2 would be a translation. It shifts the whole radical function 2 down, but it's not a reflection. Also notice example H. H is probably the most likely to get missed of these examples. It's kind of tricky. The reason is, it is a x-axis reflection, but it looks like there's no brackets here. At least the way it's written, there's no brackets. However, the x is to the power of 3. So order of operations dictates we need to deal with the exponent of 3 before we concern ourselves with the negative sign. So basically, this x input is going to be multiplied by itself 3 times. And then whatever that answer is, we tack a negative sign on afterwards. So it's almost like there's invisible brackets around the x itself. And so as such, this would actually result in an x-axis reflection. All right. Now, to talk about stretches, differentiating between horizontal and vertical stretches. Again, we're looking for an a value or some number multiplying this thing, either the input inside the brackets next to the x, or on the output outside of the brackets that contain the x. And so you can kind of look and see here in example A, 3 is our dilation or our a value. B, it's 1/2. C, it's 2. E, it's 2. G, the 1/4 is a number attached to the x, so that is our dilation. 1/4 is our a value. 5 for I and 3 for j. The D, F, and H do not have a dilation. There's no a value other than 1. F and G are a little confusing. 2 to the power of x would be the parent function. So 2 is part of the basic parent function, not a dilation. Yeah, I think those are all the traps on this page. And of course there's negative signs there. But when we look at a values, it doesn't make much of a difference. The negative signs refer to reflections. All right, so some takeaways. We now know 2 more kinds of transformations. We knew translations before, but now we know reflections and stretches are 2 more types of transformations. We also looked at reflections and stretches using function notation, and we practiced reading for reflections and stretches using function notation. I feel like I just repeated myself twice there. And I will repeat this. If you caught the Moulin reference in my slides, good on you. And if you caught the Baymax reference, good on you times 2. Leaving you with one last question. Why? Baymax is a Marvel superhero. He is part of the MCU. So why isn't he part of like the Avengers movies? That's my question for you. But this lesson's over.